Hello, everyone. That's loud. How's everyone doing? Well, good evening. My name is Vaishali Bokhio, and I'm the Interim Dean of Science. Welcome to the College of Science's inaugural Inclusive Excellence Lecture. Before we get started, let's acknowledge together the impact that Oregon State's land grant history has had on Indigenous communities. The Morrill Act of 1862 cleared the way for the seizure of nearly 11 million acres of land from 250 sovereign tribal nations to establish land-grant universities in the United States. Oregon State University is located within the traditional homelands of the Marys River Band of the Kalapuya, who were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are a part of the Confederated Tribes of Grand Ronde Community of Oregon and the Confederated Tribes of the Siletz Indians, some of whom are a part of the Oregon State community today. We deeply value their presence and contributions to the university and to the College of Science. It is our privilege and responsibility to support the success of students from Native and Indigenous communities throughout the United States. In the College of Science, we believe that science should be by all and for all, informed by a wide variety of perspectives, backgrounds, and experiences. We emphasize embedding inclusive excellence in everything that we do. We believe our capacity to thrive is a function of our ability to value and engage the rich diversity of our community members. Our future success will depend on engaging all voices, and in particular those that have not been consistently heard in the past, to answer science's greatest questions. In 2019, the College of Science launched its Inclusive Excellence Award to recognize the outstanding work of faculty, staff, or students in advancing inclusive excellence here at OSU. And in the past, both faculty, staff, and students, in all categories, we have given this award. This award was an action item in the college's 2016 Diversity Action Plan, and since its inception, the Inclusive Excellence Award has recognized faculty, graduate students, and student organizations. With the launch of our Diversity Action Plan in 2021, we have expanded this award to include an Inclusive Excellence Lecture. This yearly lecture will not only celebrate the Inclusive Excellence Award winner from the prior year, but also serve as a venue to highlight our work to date in inclusive excellence, celebrate our successes, and address our future priorities in the work that we still have to do as we elevate equity, access, and inclusion topics within the college and the OSU community. I would now like to introduce the College of Science's Director for Equity, Access, and Inclusion, Cameron Kadaoka, to give our also inaugural annual address on diversity, equity, access, and inclusion in the College of Science. Cameron is not able to be here in person today. We will play a pre-recorded video with Cameron's remarks.
Good evening, and thank you for joining us for the inaugural College of Science Inclusive Excellence Lecture. While I regret not being able to be there in person, I am nonetheless excited to have Marilyn Mackiewicz as our inaugural Inclusive Excellence Award lecturer. Tonight is an opportunity to acknowledge the great work that has taken place here in the College of Science over the last year, and to celebrate our Inclusive Excellence Award winner. Before the introduction of tonight's speaker, I want to take a few moments to highlight, celebrate, and recognize the great work taking place here in the College of Science. All across this college, in ways that impact students, faculty, and staff, work has been done to increase belonging, to provide for opportunities to learn and grow, to support a diverse community, and to work on systemic change to make the College of Science more equitable, accessible, and inclusive. The College of Science launched the 2021 Diversity Action Plan, or DAP, embedding equity, access, and inclusion in the fall of 2021. Over the last year, the college has developed its 2022 strategic plan, extending the reach and impact of science. A major part of the implementation of our DAP was to ensure its complete embedding and integration into the college's strategic plan. And I'm happy to say that I believe we achieved this integration successfully. I invite you to view both strategic plans on our website. The Equity, Access, and Inclusion Leadership Council, along with two subcommittees, the Gender Equity Committee and the Equity Data Collection Committee, have worked on implementing many actions in the college's DAP. We have investigated holistic admissions for grad students, developed equitable rubrics for awards, launched the Gender Equity Leadership Fund, and successfully attracted funding to support research opportunities for diverse students. There's also been great work done at the department level in support of our Diversity Action Plan. For example, you'll hear more about this work from Marilyn Mackiewicz, but our chemistry department has spent considerable time and effort in developing belonging and a sense of place for their students. As we think about opportunities for learning and growth, the Department of Integrative Biology has provided its faculty and students with ample opportunities, including several reading and discussion groups over the summer, focused on diversity, equity, justice, and inclusion. They've also worked to bring trainings and workshops to their faculty, including workshops on topics of sex and gender in the classroom, and ways to decolonize research. The Statistics Department has also worked to bring learning opportunities to their faculty, including a workshop on social justice education titled Critical and Inclusive Practices for Faculty. Significant work has also been done to support our diverse communities locally, regionally, and nationally. Faculty in the Biochemistry and Biophysics Department, along with other collaborators, were involved in the development of techniques and approaches for teaching biochemistry to the visually impaired. Regionally, microbiology faculty Rebecca Vega-Thurber and graduate student Savannah Leithold developed and delivered the Pernod Microbiology Camp. The STEM camp focused on engaging historically underrepresented youths in the field of microbiology. Nationally, our physics department participated in the American Physical Society Idea Network of equity-minded physics departments, providing support and contributing ideas to help other physics departments advance their own EAI goals. To effect change at a systemic, procedural, and policy level, other units took important steps. For example, our math department has developed processes to make their National Honorary Mathematics Society, Pi Mu Epsilon, more diverse and inclusive. And in the Dean's Office, we've developed policies to compensate students who participate on college-level committees where they are contributing an EAI perspective. And we've updated the college's search rules to better embed equity and to ensure new hires embody our values of equity, access, and inclusion. While this is only a small sampling of the work that we have done at all levels of this college, it speaks to the breadth and depth of the commitment to the collective strategic effort required to break down barriers in science and make our community more welcoming. We also have lots of work to do. In the coming months, we'll be initiating an iterative process to establish holistic admissions across all of our departments for graduate students. We'll be examining gender equity across a variety of vectors. We'll be delivering equity-based professional development for graduate TAs and building out a new research program to support those who have traditionally not had access to research experiences. I look forward to working with each and every member of the College of Science as we work to embed equity, access, and inclusion into everything we do. With acknowledgement of the work ahead of us, we are honored to be celebrating Marilyn Mackiewicz and to hear her lecture, Empowering Cultures of Belonging, Thriving, Innovating, and Solving Global Challenges. Thank you for coming and enjoy the lecture.
I would now like to welcome Assistant Professor of Chemistry, Marilyn Mackiewicz, to present her talk titled Empowering Cultures of Belonging, Thriving, Innovating, and Solving Global Challenges. Professor Mackiewicz, who started at Oregon State University in 2020, is a recipient of a career award from the National Science Foundation. The Mackiewicz Lab consists of modern-day explorers of the molecular world and architects of nanoscale materials, with research focused on the development of nanostructured materials for applications that relate to human health, the environment, and energy. Please welcome the 2021 College of Science Inclusive Excellence Awardee, Marilyn Mackiewicz.
All right. Well, thanks for that warm and long introduction. I think she took some minutes off of that. I did say keep it short. I don't like always being the focus of things, which is very different today. I'm excited to be here, and I was so excited to hear all the things happening across the College of Science from many different departments, and I look forward to the next person that's going to be on this stage telling you about all the good work that we're doing in their departments and in the College of Science. So I thought what I would do today is start off with the power of words, vulnerability and advocacy, transdisciplinary science, resilience, and inclusive leadership. Now, these are pretty easy for me to talk about. These two parts are not so easy because I often don't share a lot of personal things about myself, except when it's with my students and the people that I mentor. So you're going to get a view into a part of me that I keep to myself most of the time, not in a big public forum like this. Okay, so we'll start with the power of words because they can profoundly impact you in a positive way and negative ways. A friend of mine saw an article written by the College of Science, I think last year, and we grew up together in my home country, and she messaged me and she said, "You turned out to be just as big a nerd as we all thought you were going to be." And then she said, "I wonder what Principal Ishmael would say if he saw you today." Now, she recalled a story that I told her years ago. It's been over 30 years of the story about I wanted to get into the science class. And this was the only science class at the school. And I had done pretty well up to that point, and I was moving to a different grade level. And my aunt went to the principal's office with me, and she said, she needs to get into the science course because she's going to be a pharmacist, and these are the courses you need for pharmacy. I don't know how we knew about that because my aunt didn't have even a high school education. And he looked at me and he said, "You're not smart enough to do science." Now, I didn't think anything about it at that time, but I think back about that thing because I remember it so clearly in my head, and I don't know why, but it's there. And I thought, well, he didn't look at my grades. How would he know? Because I was an A student, but he thought I wasn't smart enough to do science. Well, I did get into the science classes, and some of the boys in my class couldn't read, and that was pretty surprising. How could I not be smart enough when some of my colleagues couldn't read in class, and my English teacher used to help them during lunchtime? Now, that's not the important part of the story. The important part of the story is the advocacy from my aunt. Because if she didn't do that, she was a vendor that worked outside of the school, I wouldn't have taken my first chemistry class, and I wouldn't have become a chemist. Okay, not be emotional, all right? Okay. This is hard. This is the part that's hard, right? All right, this is something more recent. People like you cannot think you can come here and transition from non-tenure track to tenure track. That's not true. Non-tenure track people can transition to tenure track. They can do it here at Oregon State University because there's lots of possibilities and opportunities here. Now, these words can have lots of impacts on you. They can stop you in your tracks, right? You can believe in them and never do anything. Or, if you're like me, you use them as fuel because I believe I can do these things. So somewhere along, early in my development, back to when DNA was being put together, there must have been a code for stubbornness because that's what I have. I'm pretty stubborn. And when I know in my gut there's something right that I have to do, my stubbornness kicks in. And my grad advisor will tell you that I am stubborn, but in a good way. All right, so the power of vulnerability. I share these stories in the next few slides because they're important. I believe my stories are important, and my students help me see that. And I think that your stories is just as important because they do impact the students you teach in classroom. So I would never be able to share these stories if my students didn't tell me that stories that I share impacted them. Okay? So I want to tell you where I grew up. So if you hear me today, you'll hear some weird accents, but in my head it's very American, but it's not really American at all. I'm Trinidadian. I grew up in Trinidad and Tobago. I grew up in Chaguanas, which is a native Amerindian name. And I know I have some Trini people in my audience here representing. Trinidad is very diverse in that we have most of our people come from Africa or East India. So I'm East Indian, but not really East Indian, and I'm West Indian, and I'm Trinidadian. I'm everything. It is the land of Calypso, so a lot of people go to Trinidad for Calypso and for Carnival. And we have gorgeous, salty beaches that you can smell a mile away. And I can still remember what the beaches smell like as we get close to them. And if you're like me and you go to the beach, there are vendors everywhere, and they sell deep-fried shark and bake, which is so delicious. But if you're not a fish eater or a meat eater, you can get doubles, which is made out of garbanzo beans, and a tamarind chutney, which is just as delicious. And you can wash this down with local beer. Now, the thing about Trinidadian people is we're kind of crazy and we're loud, but we're very community-centered. So it took me a very long time to realize what was wrong with me in America. And that was, I'm very community-centered, and it's difficult for me to be very individualistic. Someone needs to teach me that, or I don't know. But you'll understand that in the next stories, I'm very community-centered, and that's what drives me. So this is why I'm telling you where I'm from and what drives me. So my parents, when I was 16, decided I had no future there. No matter how beautiful that island is, they recognized I wouldn't be able to go to the only university in the Caribbean, the University of the West Indies. And even if I could go, we couldn't afford it. So they sold everything in our house, everything. And we moved to the Bronx in 1992. And I went to 2 years of high school in Adelaide East Stevenson. And then I went to Hunter College in the City University of New York. And there, I learned about research from my English major friend. I said, what did you do this summer? And she said, I was in a research lab. And I said, you can do that? And so I joined a research lab because I thought I needed to do research in order to be better in chemistry. And you'll say why I needed to do better in chemistry. But that research experience impacted me significantly. And that's why you see a lot of undergraduate students in my lab. At Hunter, I got a degree in psychology and chemistry. I took one too many psych courses, and then I thought I should get a degree, which comes in very useful nowadays. I then went to Texas, so from New York to Texas, very different life, culture, and I got a degree in bioinorganic and organometallic chemistry. And while I was in grad school, I got an NIH recursion grant, which supported my graduate research. I graduated in 2005, and my partner, Ryan, and I got jobs at Intel. He was there a year ahead of me. 6 months into my little gray cubicle, I said, I think I need to go back to academia, even though I told everybody I'm going to go to industry. I was wrong. You can be wrong. So I left Intel, and I thought, okay, I need to go back into academia. Where can I find a postdoc? And the only thing was at Portland State University, because I was geographically constrained. And I started doing nanomaterials chemistry, even though I didn't even know what a nanoparticle was. I actually Googled it before my interview. You have to be prepared. So I left Intel, started nanomaterials chemistry with a young assistant professor who I loved a lot. He was a great boss to have. And then a year into my postdoc, he left and he went to Denver. And he said, do you want to come? And I said, I don't think so. So I stayed working as a postdoc remotely. And then I decided, well, you have to do something with your life. So you have to put proposals together because academia is the route for you. So I wrote a small pilot grant that allowed postdocs to transition into faculty. And I became a research assistant professor. Now, I didn't know what that really meant. But my life kind of goes by the seat of my pants sometimes. And I started doing my own research, and I was so excited about this. And I spent about 12 years doing this at Portland State University. So up to this point, all I saw was myself as a scientist, and that was about it. Until students in the LSAM program, Lois Stokes for Alliance for Minority Participation, asked me to come and give a plenary lecture. And of course, I'm giddy, because you get asked to give a plenary lecture, and you're going to talk about your research. Except that's not what they wanted me to talk about. They wanted me to talk about myself and where I came from and how I got to where I was. Why? But I did this, and after the talk, I had so many students come up and talk to me and tell me about their experiences, which mirrored mine. So this changed everything that I was going to do as a scientist. I promised I wouldn't get teary. Anyway, in 2017, I developed a course called Empowering Women and Marginalized Students in STEM. I needed to develop this course. And it was actually because someone pissed me off and I said, listen, women belong in science and I'm going to design this course to prove that to you. I got an NSF and an NIH grant, so it took me a while to build my lab, get grants, and then I thought, I want to do more. And I'm looking for a place to do more, and I ended up in Oregon State. By the way, in 2010, I interviewed here, but I didn't get hired. And then in 2017, I also interviewed virtually, but I didn't get an offer to come on site. So I thought, it doesn't matter. You won't be there, no matter how much you like that campus. But in 2020, I got a little email that changed everything. So when most people see me, they see success, grants, publication, great mentor, good at teaching, but there's so much we never see about all the work that goes in towards success, okay? And all the failures that happen along the way, which I don't think are failures, just like there's no bad experiments. Here's the personal stuff that I can fit on the slide. So I tell my students, because they think, you got a PhD in chemistry, you must be great at it. No. Chemistry was really hard. I got a C in Gen Chem, and I thought that would stop me. When I got the D, you think that would stop me. But as I said, DNA with stubbornness. I retook the OChem, got a B+, so it keeps me going. F in physics, 3.25 GPA in college, and somehow I managed to get into Texas A&M University, study PhD. And that was because of the research experience. I spent 4 years doing research as an undergraduate student. Got into grad school, got a C. A C is a no-no, got put in academic probation. That's not good, and the C was in my grad advisor's course. Ouch. She kept me. She didn't abandon me. That's what good mentors do. And I published 10 papers as a graduate student in 4.5 years. You can do research, and the grades really doesn't matter. Pass the classes, learn what you need, okay? I mean, it does matter. Don't get a B-, okay, to the students. All right, this part of the talk is for the students, by the way. I forgot to mention that. Okay. And I had a lot of things going on. I built my lab with $75,000. That was my startup package from that grant, a minimal space. And most of the time, I didn't pay myself, thankfully, because of my husband. And I used that money to support students in the lab when I could. That's pretty impressive. None of these are bad things. But I almost thought about quitting academia. Okay. Here's what I wanted to do with my life, and I wanted a place and a job that would allow me to do all of this. Do the transdisciplinary research I was doing, bridging chemistry and biology and engineering, okay, towards clinical applications. And I wanted to be able to give my student that experience as well. Transformative pedagogy, making classroom environments inclusive and welcome, thinking about the way we teach, more importantly, providing students with skills so when they graduate, they can get a job and they can be successful in their career. So those are the things that I'm interested in learning about and teaching. Leadership. And mostly it's inclusive leadership. How do you build cultures of belonging where everybody feels valued? When I come to places or when I talk to colleagues, this is what they tell you. I want to feel valued for the things that I do. I want to be respected. I want a sense of belonging. Okay? That's what I heard many years in my previous institution and also when I came here. So this is pretty important. And good mentorship is just as important because I wouldn't be here without my mentors. So mentors are extremely important. So remember this? A week later, I get this. Wow. Life does change with a nice little email. Okay? And I got asked to come and give a talk in the department, and now I'm here. So I moved in the middle of the pandemic to OSU, and I continued doing my research towards building materials for biomedical applications. There's different types of nanomaterials that you can build. We build inorganic nanoparticles because we want to use them for bioimaging. And we want to use them for drug delivery, sensing, and cellular labeling. Most nanomaterials never make it to FDA approval because they're extremely complex in nature. And we need to understand nanoparticle biological interactions, how those interactions and how the features of materials play a role in toxicity, if they're ever going to make it to real applications. So we focus on discovery of new materials with new properties because we want to get our materials here. But to do that, we have to design the materials using green synthetic chemistry routes. We need to study nanoparticle biological interactions and understand the toxicity of those materials, which requires a multi-scale approach from in silico to in vitro to in vivo. This is the only way you're going to really study these materials and understand them. And of course, to be able to do this, you need skills and expertise, which I'm fortunate to have really great partners to do that. So right now, my students work on tuning the shape and the size. We want homogeneous mixtures of one shape, one size. We want silver, gold, cubes. We make rods, all of these things. Composition, titanium, gold, you name it. Why? Because they have optoelectronic properties that we can use for reflectance imaging, X-ray attenuation for X-ray imaging, and currently we're working on bismuth and nickel for, the nickel is for X-ray fluorescence microscopy imaging. A lot of what we do is also think about the surface coatings that we put on the nanoparticle because we want to use them for biomedical applications. We want to use ligands or molecules that are bio-inspired, so when they go into human body, they look like they belong there. And we want to be able to take our materials and target them to specific cells or tissues inside of the body. So for materials to be used for biomedical application, they must be stable in a biological environment, bypass the immune system so they don't get rejected from the body or cause an immune response, long circulation time. They must be able to interface with tissue or cells of interest, targeted towards specific cells because we don't want them going everywhere. It defeats the purpose of some of the application, and good cellular uptake and retention. Now with these materials and some of these properties, there's a lot more that we want. We can use them to kill things, and we also want them to not kill things of interest. And I'm going to highlight one example of materials where we don't want any cell death. Okay. So this is one of the platforms in my lab. It has a lipid membrane on the surface of the nanoparticle. And a nanoparticle is usually between 1 to 100 nanometers, which is the sizes that we want to use for biomedical applications. And these materials have a lipid membrane, lipid because it would provide our nanoparticles with stealth character once we put them in a biological system. We think about the way we're going to coat these materials because we want to minimize waste, and we don't have to purify the materials, which it causes more waste. So we layer the nanoparticle by calculating how many of the lipids we need to make a monolayer, and we want a bilayer because we want these to be water soluble. But these membranes can rearrange, and we don't want that because if the membranes rearrange, the lipids could come off. Then if they're in a biological environment, they can interact with biological things that we don't want them to interact with. So in our assembly, we start with our naked nanoparticle. We add this ligand called sodium oleate, and then we encapsulate them with little membranes that coats all of the nanoparticle. And to stabilize this membrane, we use a thiol, which has a sulfur group that covalently attaches to the gold surface. And this thiol has a long tail that interdigitates in between a lipid bilayer. Now, this is not the best cartoon, but we're not artists. We hope to be, but we're not artists. And what this thiol does by interdigitating here is it pulls the membrane in this tight little packing arrangement, almost like shrink wrap, so that the nanoparticle surface won't be exposed to anything else. Okay? And we know this from a lot of different studies that if we expose these materials that, with chemicals that would oxidize the gold from gold 0 to gold 3 and decompose the material, that the oxidants cannot penetrate through the lipid bilayer to etch away the gold or oxidize it and degrade it. So this little membrane that we anchor shields it like candy coating, although you could eat candy coating and it disappear. So maybe that's not the best analogy. A little bulletproof vest. That's the way I like to think about it. Okay, so we can do all kinds of things with these materials. My students thought, well, could we stabilize other materials that could be used for biomedical applications, but these are prone to surface oxidation and toxicity. And these are my undergraduate students over the years that I've worked on my silver nanoparticle project. And these are my high school students. Yes, I take high school students, and they're just as capable in the lab as some of my undergraduates. And this is a master's student from Stacy Harper's lab who learned about our nanoparticles and went from zebrafish toxicity work to making materials in my lab. So that was pretty exciting collaboration between our groups. We wanted to stabilize silver. And silver is important because it's a good antimicrobial agent. In fact, they're used in all kinds of products that you use every day, but you don't even know that they're in there. So for example, food packaging has silver materials in there because it kills bacteria. Makeup, anything that says odor-free likely has silver to kill bacteria, so it doesn't smell. Every year, about 500 tons of silver is produced for these different applications, and guess where they're going to go? In the environment. So now you want to think about the environmental impact and toxicity of these materials. And we know that silver metal ions themselves are toxic to humans. But what we didn't know from the literature is whether the nanoparticle itself is toxic. Is it only silver, or is the nanoparticle safe? But when you're trying to study these materials, these silver nanoparticles, the problem is they're always oxidizing, so silver comes off. So if you're trying to do toxicity studies, the silver ions is always present, which means you can't really study the toxicity of the nanoparticle and how the shape and the size influences toxicity because of this. So you have to come up with a strategy to prevent silver ion from leaching, then study the shape and the size effects of the nanoparticle itself, which our membrane allows us to do. So for the first time, our membrane allows us to coat a variety of silver nanoparticles of different shapes and sizes, including rods, little spheres, little cubes. We can make these and coat them with a membrane, or triangular plates. And this technology allows us to prevent silver ion leaching, and we can now look at the toxicity of the silver nanomaterial itself. Okay. Of course, I have my wonderful partner of 15 years. We've been doing this work for as long as I've known her. And we look at all different types of materials that we build. Without her expertise, we're not able to do some of these studies that we want to do. This is a great partnership. We design different silver nanoparticles with different coatings, and these materials here release silver ions, whereas these materials over here, these are our hybrids, they don't release any silver ions at all. And we know that if these release silver ions, they're not going to be as stable, and likely they're going to be more toxic compared to these nanomaterials over here. And that's exactly what you see when you look at percent mortality over concentration with a variety of these nanoparticles as spheres or triangles, that the nanomaterials, these that release silver ions, have an increase in mortality. Whereas the hybrid nanoparticle, the sphere, you see very low mortality because it's not leaching any silver ions. When you look at triangular plates, you do see mortality. You see more mortality with these nanoparticles and little to no mortality with the triangular plate where no silver ions are released, which is pretty good news for us. So these are biocompatible. But it doesn't explain if shape or size can induce toxicity at all. We went back and made a series of hybrid nanoparticles from 20 to 100 nanometers. And we looked at the toxicity, and we noticed as we decrease the size, there's an increase in toxicity. So even though if you shield a nanoparticle from toxic silver ion release, these can still be toxic. And that's really important to know. We wanted to know why materials are toxic, what's governing toxicity. We did some work with Joe Bio, another wonderful colleague who does some frequency gain spectroscopy. Don't ask me how it all works. It's very complicated, but I trust him. And what he looks at is the nanoparticle interactions with membranes. And from these studies, we know that the smaller nanoparticles, they're so easy to go through the membrane without any problems whatsoever, which means that more of these small nanoparticles could go inside of the cell. Compared to larger nanoparticles, it takes more energy. The membranes warp around our nanoparticles for them to get inside of the cell. So it looks like there's a concentration-dependent toxicity based on the size of the materials. And now we're examining using SFG spectroscopy and correlating it with the toxicity work in Stacy Harper's lab. And we're looking not just at the spheres now, we're seeing interesting things with spheres, with cubes, with triangles, and we're going to start looking at the rods. So lots of work still to do. We know that from our work overall, with lipid nanoparticles and other ligands we put on the surface, that this impacts the biocompatibility of the material. It also impacts the stability and how they interface with biological systems, as well as the toxicity and their cellular uptake and viability. From our silver nanoparticle work, what we've seen is we're able to identify features of nanoparticles that can lead to toxicity or drive toxicological outcomes, which allows us to guide policymakers regarding the use of silver nanomaterials in the commercial products that's available and how those might impact human health and the environment. So all of these studies are important for us, and I'm pretty happy that our nanomaterials are still very biocompatible. We do have to pay attention to shape and size going forward. So I mentioned that we want to discover new materials, and then we want to put them in the clinic. That's what my students are excited about. That's what I wake up every day thinking about, a nanoparticle being used for something. Now, nanoparticles are being used. You think about the COVID vaccine, drug delivery, other types of drug delivery, lipid nanoparticles are used all the time. But metal nanoparticles, very few of them have made FDA approval because of their complex nature. So we have partnered with several different people, developing nanomaterials for a variety of applications. And it's exciting to work with these people because I can see how we can move closer towards clinical application. So we design materials for macular degeneration and glaucoma with OHSU KCI Institute and the Devers Eye Institute, and we have work going on to develop X-ray imaging agents to target triple-negative breast cancer cells. We also do some non-nanoparticle work with Alzheimer's disease to try and develop diagnostic assays to screen therapeutic drugs. So I only have time to highlight the one partnership with OHSU because this is the work that was funded by the NSF Career Award. My partner David Huang and Trevor McGill, they're both at OHSU. I didn't know them before. And they sent me an email, and I figured, okay, I'll respond to this email. And we had a meeting, and they wanted to talk about nanomaterials for an application related to macular degeneration. I'm always open to meeting new people. David is the co-inventor of optical coherence tomography. So if you've ever gone to the optometrist and gotten an OCT scan of your eye, this is because of his invention when he was a graduate student. And Trevor works on the development of therapeutic stem cells. The technology that, well, let me just step back a little bit. For macular degeneration, I don't know how much you know about it. 80% of people have the dry form of the disease, and about 20% have the wet form. And there are some therapeutic options for people who have wet macular degeneration, but for people who have age-related macular degeneration, the dry form, there's no therapeutic treatment, and there's a lot more people with this. Especially if you have diabetes, then you might end up getting a macular degeneration, which results in loss of sight. And there's no treatment for it. However, stem cells is a good potential therapeutic approach. By taking embryonic stem cells and transforming them into retinal pigment epithelium cells, or RPE cells, you can then take these cells and inject them into your eye. And what they've seen from clinical trials is that you can rescue vision loss. So if you can replace the dead or dying cells, you can rescue vision loss. How cool is that? Here's the problem. In order for you to study where these cells go in once you inject them to the eye and how long they survive, you need to do post-mortem histological analysis. So you've got to sacrifice the animal, section the eyeball, and look at where the cells go. Okay, so if you want to study this over a year, you can't section the eyeball, okay? Which means you have to do multiple animals and then figure out how to take that information and reconstruct it into a three-dimensional map to look at what happened to the cells. and that's time-consuming, expensive. So we need a technology to be able to label these therapeutic cells and then track them in vivo in real time over a long period. So that's what I'm working on. OCT is a really good technology to image inside of the eye because it's translucent, it's non-invasive, and you can just sit in front of the instrument and then take a really quick picture. I just did this with my optometrist. So I was going to put my eyeball up there, but I didn't have the image. If you have wet macular degeneration, what you notice is these nice layers of cells inside of the eye get disrupted because you have loss of cells. So OCT is the instrumentation you use to determine if you have glaucoma or macular degeneration. Okay. This technique is non-invasive, but it does require contrast agents if you want to track that single cell once you inject it inside of the eye, which you can't do because you can only see things at micron scale resolution. And this technique requires high scattering. We think gold nanoparticles could be able to do this. So you can use the scattering of the nanoparticles to label the cells and then track them with this technology. So with our nanoparticles, we have already demonstrated that we can get them up into the cell without killing them. We know how many of the nanoparticles get into the cell, and they're located into the cytoplasm of the cell surrounding the nucleus. So we can get about 3,000 to 5,000 nanoparticles in a cell without killing them at all. I'm sure we can get a lot more. And they're very biocompatible. So this is all the data I'm going to show you because this is another 40-minute presentation. And I'm told I can't trap anybody, right? Hey, they took some time from me, Gabs. I got to catch up. All right. So I can't do any of this work without my students. My success is because of my students. And for the first 12 years of my life, maybe 13, as an independent investigator, all I had was undergraduate students. That's it. No grad students. This is the first time in my life I had grad students. I have 4 of them. I'm so excited. But these students started in my lab for 1 year, 2 years, 3 years, until they graduated. Majority of the students stay beyond 1 year. 50% are identify as female, 50% male. I didn't pick them. It just showed up that way. The numbers are the way they are. And they come from very different backgrounds, different undergraduate degrees. Some were paid by research programs, and a great majority didn't get paid at all, unless I gave them some money. Of the 48 students in that time period that I calculated, only one of them did something non-STEM degree related with their career, but did get a STEM degree. Everybody else got a STEM degree and pursued a STEM profession. Okay, so this must be normal. This happens to everybody, right? Turns out I thought it did, and there had to be something I was doing in addition to giving them the research experiences that make them stay. Which undergrad wants to work for free? Okay, it's challenging, especially as undergrads. So I switched to the power of resilience. And I'm gonna go a little faster now, because Gabs is telling me I have 5 minutes. So it's important to develop good scientists, but this is not all we need. Over the years, students ask me, how do I navigate interactions with scientists, non-scientists? How do I ask for new projects? Dr. Mack, I'm sick of counting cells and feeding the worms. Okay, these are the problems I deal with. How do I handle conflicts, imposter syndrome? I feel undervalued, okay? How do I network and find mentors? How do I talk to my professors? Everybody seems smarter than me. Do you hear that? You must hear that, right? It's not just me. I don't belong here. So I know what that feeling is like. So when I was 38, I took a negotiation workshop, and I sat there with all these chairs in different departments and faculty, and I thought, wait, how am I 38 and I'm now learning this skill? What if I knew this as a postdoc? What if I knew this as a grad student? What if I knew this as an undergrad? I could ask for things that I needed, and maybe things would be a little bit easier on me. So I decided we're going to talk about these things. And we developed a summer workshop. I made it more formalized in the group. We talk about research, literature, and professional development. I cover interpersonal skills, networking, negotiation, leadership, communication, and active listening. And then we talk about writing. We do writing. Okay. This then developed into the full course for the capstone. And we cover more than just these topics. We cover how to deal with microaggressions and how to build your confidence. So every time I survey the students and I ask them, what do you think you need to strengthen your career? What do you think you need to be successful? here's what they tell me. And I'm never surprised anymore. And I still collect this. It's still going. So I worked on developing the capstone covering that. And then I built the programming arc for the enrichment for sophomores in the Build Ex Edo program. If you don't know about this, it's a $44 million program that supports undergraduate research in biomedical field. And I work on sophomores because I want to build their professional identity so when they go into research learning environments, they can advocate for themselves. They could see themselves being there when no one else looks like them. So I had to take all of this and distill it down, because Mike asked me to, into the Careers in Chemistry course. This is a 6-credit course, by the way. So I'm distilling down a lot of the content and focus it on the Careers in Chemistry, and I also work on the 320X, all of the skills here. So these are the amount of undergraduates, even high school students. We have high school students coming into the lab doing research, and they get the same level of professional development. And I'm tracking what happens with our students in the next 2 years or 3 years when they graduate. Okay, you need good mentorship, scientific identity, and a professional identity. And I feel this is what has helped my students with success and retention in STEM over that 12-year period. Okay, inclusive leadership. And don't run away, okay? All right, inclusive leadership starts with the power or the spark to do better. Okay? It means supporting each other, learning and growing together to contribute in meaningful ways, elevating others with softer voices, because we all have the power to do that. Making a change within ourselves and in the community around us. Okay? This is what inclusive leadership means. When we think about diversity, we think about physical traits, appearance, tone. Okay? These are the things that come to mind. But there's so many different dimensions to diversity that we often don't think about. Work ethic, race, sexual orientation, gender, family status. Most of us are comfortable representing ourselves, but some subset of us is not comfortable. And if we're hiding ourselves, we're not living up to our true potential. And also, it takes so much effort to hide who we are, we're not being productive. If we are diverse, we're innovative and creative and we can solve big problems. But in order to sustain this environment, we need to embed inclusive excellence, where we have enhanced engagement, people are happy, they're productive, enhances morale, increases trustworthiness. You can't get anywhere without connection and trustworthiness. But if we are to be good in this and we're to be good in this, we have to think about equity. Because not all of us have the same experience, and some of us will need more skills or a boost in our skills. Okay, so how do we do this? So we started in 2020 with the EJI committee, and Doug Kessler took over and was the chair of the committee. We separated into 3 groups, and I was involved in community engagement and practice. I recruited some faculty members. The incentive was wine if they joined the committee, and let me tell you, it worked. But honestly, I think it's because they care. Okay? They care about our community. And I also recruited some students who have been involved in this community. In order for me to lead this team, I needed to get to know where they are in the leadership continuum. Are they on the unaware stage, the aware stage, active advocacy? Here, you don't even know there's a diversity problem, or you think it's compliance related. Here, you understand that there's problems, but you might not know what you need to do. Here, you understand the problems and you're actively doing things. And advocacy is where you're making big systemic change, okay, in policy and procedures. So I asked everyone to take an implicit bias test, an inclusive leadership test, so we can see where they are, and also a little innovation styles assessment, because I like to learn about people I'm working with and what skills they have in the team, because we have to move forward together. The next step was to teach them about strategic doing. I love strategic planning, where you think and then you plan and then you do. I'm kind of like this because I get impatient, so I do think, plan all at the same time. And the reason for teaching this is because this work can feel overwhelming. So how do you get people to do little things that have meaningful impact? And I think this is a good process. So what we do is we think about all the things that we could do, all the things that we should do, and what we can actually do in a given time frame. And so this is what we worked on. We come up with a bunch of things, and what we want to do is find something that has high ease and high impact. Okay. So we had several different things. Are you feeling lost? Highlighting research and teaching faculty, because students didn't know the difference between the research faculty, the teaching faculty. Honoring our emeritus, because one of the things I learned from students is about the dude wall outside the first floor in the chemistry department. Honestly, I just missed the dude wall, so I had to go look for this. And then transform our entryway because of this. We wanted to also highlight our alumni and find a creative space for students. My dentist complained to me that the chemistry department didn't have a place for undergraduates to study. So he used to sneak into places. Okay, we can't have people sneaking into places. So we found a place in the basement. Okay, hey, this is important. It's in the basement, and this is where we had our emeritus faculty. And they gave up their space in the basement, so we can transform it into this. This is by far the most modern space in Gilbert Hall. Okay. And this space was designed with the help of Citlali Nieves-Lyra, an undergraduate in our department, who helped in picking out and choosing things that students would like and what a space for students would be that they want to go there. And we couldn't do any of this work because you can't even hammer anything without talking to Rusty. So Rusty, even though he's not on our committee, he's on our committee, and this is called the triple point. Whatever phase of your education you're in, you can be here. Okay. We also have a new slogan and a logo designed by our students, where diverse minds inspire endless innovation. This was a whole competition. Faculty submitted, some faculty didn't get voted for, the students won. Okay. It's important. The dude wall came down, and what we wanted to do here is highlight our faculty and who we really represent now. So this is Dr. Gable. I love this because he looks Time magazine-like, right? And we talk about what their research is, their mentoring philosophy, and there's a QR code that links to the website. We also want to highlight our alumni. So if you're an alumni, guess what? We'll be calling you up. So we can highlight, because students want to know, when I graduate a chemistry degree, where am I going to go? How successful is our alumni? And we also wanted to incorporate our emeritus, because they are the history of our department. So it's important to talk about the science that they did and also the service that they did. And this was a lot of work, because all we had was pictures, and we had to Google stock, go through history archives, and Luann, Lou, Mike, Kevin, everybody helped with this project. Now, we started putting this up, and then we realized, oh, we have too many pictures. We got to space them out. So we're taking some down and rearranging them, because it doesn't quite give us that art gallery effect. Lastly, Doug and I worked on an equity audit in the department, because we need to change policy practices and process. So we did an equity audit, and from that, we developed EJI charges for every committee in our department, which allows every committee to look at how they operate, their policies, and their process with a diversity equity lens. And I can already tell that progress is being made. Maybe the committees don't know we're watching them. We're watching you, okay? And one of the things we noticed is the awards committee created a new process. And I know this, David didn't think anybody was watching. We were watching you, David. So as we see our colleagues do important work in the department, it's important to recognize their work. And we're building a little surprise for everybody, and we'll tell you about that in the future somewhere. All right. We have a lot of work to do, and I'm not going to even go through this. So prepare yourself, EJI committee. I want to thank all my students, the College of Science, Gabs, Cameron, my colleagues in the chemistry department for being so welcoming. I have loved my first 2 years here, and I hope to stay if you have me. Mike and Wei, because none of this is possible without funding from the chairs. And Roy and Mike made it very easy for me to choose to stay and come to OSU. Obviously, I wanted to come here since back 2010. But here's the thing. My non-tenure track experience gave me a whole window into that life that makes me who I am and what drives me. If you ask me, would you change anything? No, I would do it all over again because I think I'm smarter, creative. You know, I think about things in a different perspective because of that experience. And my good colleagues, Mas, my mentor, Doug, because with him, I see what I'm capable of. Rich Carter, David, Chong, you guys are great colleagues, Kyriakos. And of course, funding, I need funding, so must thank them. And my partner, because he buys amazing snacks, and this is why he thinks my lab students stay. It's a snack buying. And with that, thank you for staying and for the honor and privilege of your time today. There's London style. Thank you. Oh, thank you. It is so, it smells so nice. I know we're over time, and I'm happy to answer any questions if you have it. And I will stick around outside if you're not, interested in asking a question up here. But you're sticking around, so I'm answering questions. Just student. How do they enter the body? Well, there's lots of ways you can get them in there. If you wanted to do something with the eye, you can use eye drops or you can inject them in there. But most people try to do them intravenously through a vein. Did that fully answer your question, Remy? Okay.
We probably have time for one more question. I definitely want to allow folks to take off. It looks like Stephanie Ramos over there. Okay.
Great work, Marilyn. My question is, you didn't mention, but you had on one of your slides Don Mason as the hidden. So I just wanted to ask, you didn't mention it, but provide any context for us as the audience.
All right, so you saw a lot of faces in my slides. Those are the people that mean a lot to me. Dawn Mason is a colleague of mine. She's more than a colleague. She graduated with a PhD from Texas A&M years before me, and I met her when she was visiting Texas A&M. And you can find her in a room because of her laugh. We became friends, and I would say she's my academic sister. And she does have permanent residence in my head, because when there are things that I don't want to do, she's in there saying, do it, right? So she is in there saying, do it, and she means a lot to me. And one day I'd like to have her visit here, but she's very special, and when I feel like I can't do this, I have my people to go to, and she's one of them.
Let's give Marilyn another round of applause. Marilyn, wow, that was empowering and inspiring. Marilyn demonstrates inclusive excellence in everything she does. When I became interim dean, I got an email from Marilyn which said, take a deep breath. You got this, dean lady. I loved that. Thank you all so much for coming today. Really appreciate your time and hope to see you at another College of Science event. Good night.